Okay, so I've got this bracket here welded onto, I don't know, a column or something. And so the actual, it's two separate welds here going on. Obviously, they're equal size. So the centroid of the weld group is just going to be right there in the center there. The variation of the load that we have here. So we got this load F here, and we're going to imagine three different scenarios. One in the situation where the load is static, and the failure and the criteria that we're trying to go for is that the maximum shear does not exceed 0.3 of the ultimate strength of the weld electrode. So that weld electrode is a E7010 electrode. So that would have an ultimate strength of about 482 MPa, and it'll have a yield strength of 414 MPa. And the welds that we're talking about, so we got a 15 millimeter leg size on those welds. We can assume they're fully returned because you'll see here, they go like this, and then they wrap around a little bit like this. They wrap around a little bit like that. So basically, what I'm going to do there is say that the wraparound part is not contributing any portion of the strength of the weld, but it does allow us to use the entire length of this little segment here, the 100 millimeters, as the effective length. And then so if the load's static is the one failure criteria. And then we got two fatigue failure criteria. One where we have got the load varying from 0 to F, and then that's going to go for a fatigue safety factor of 1.5. And then we've got the other failure criteria where the load varies from negative F to F, so it's pushing and pulling on the bracket. And again, still designing for the same fatigue safety factor of 1.5. My skin got a little cut off there, but that's supposed to be 1.5. So again, we can assume return to welds. So our effective length is just going to be 2 times the 100 millimeters, so 200 millimeters. It's a 15 millimeter weld. So for H. So our throat thickness there are T values. That's going to be 0.707 times that, so 11.61 millimeters, which gives us an effective area of 2,121 millimeters squared. So the way this loading is going to work is that it's an in-plane loading bending situation, right? So this is going to cause like a torsional type stress distribution. That's because we got the weld group here. It's acting in this plane, and the force is just still in the plane, just offset. So that's torsional and direct. So let's start with the direct. So the stress caused by the direct shear, are tau prime. That's just equal to the force divided by the effective area of the weld. So F divided by the 2121 millimeters squared. So that gives us 4.715 times 10 to the negative 4 per millimeter squared. F is our stress. So plug in some plug in some value of newtons in there, and we'll get newtons per millimeter squared. So this will be MPa. So our directionality is, and when I say directionality, that's basically you know, that's us saying that the stress that would be caused there would be equivalent if the force was just acting in that direction. So that's going in the negative y direction. So yeah, we're pulling downwards. And we're going to need to worry about the torsional as well. So if we have the torsional, we need to find J. So there's a couple of ways to go about that. One way, if you remember that when you rotate, when you're trying to find the J for a cross section, rotating that cross section doesn't change its J. And it's just because, you know, rotating the cross section changes its IX, or, you know, its IY. But J is just the combination of those two, and the way it kind of works out is that as long as you're rotating the you know, an element of a cross section about its centroid, the IX component decreases by the same amount that the IY component increases. So the J stays the same. You know, so you know, a shape that looks like this. Okay. A shape that looks like this is just as capable of resisting torsion as a shape that looks like this, or a bit too far. As a shape that looks like this. You know, they're equivalent there. So the J value for something that you know, is kind of two lines that are separated is equivalent to, like, if we rotated one of those lines about its centroid and kept that the same, or rotated both those lines about their centroids. Now, kind of three ways we could go about this. We could do it directly. So the direct approach, you know, we've got, we have our cross section here, got the centroid here. So we know that between the gap there is 250. Each of these is 100. So therefore, the distance between the centroid of the weld group and the centroid of each of these is just half 100 plus half 250. That's 175. So we can just figure out what the J would be for the, you know, each of these individual groups, and then add that up. So generally speaking, when we're doing, you know, we're trying to figure out what that would be. J is equal to X, Y. That having been said, when you have a long skinny thing that's oriented in one direction, basically this prime for those, you know, our J prime for that's going to be equal to B H cubed over 12 plus HB cubed over 12. So basically, when one of these is long and one of them is thin, we usually neglect the one that has the thin value cubed, because basically it doesn't contribute anything to that. So for this one, our J value, basically we can calculate what our J value is by calculating the J value of this and adding it to that, and doubling it, because it's going to be the same as the one below it. So 2 times the 100 millimeters cubed times the 10.61 millimeters for the thickness, the throat thickness, divided by 12, plus our 100 millimeters times the 10.61 millimeters, so or the area of that segment, times the 175 millimeters squared, which is the d, our distance between the centroids there. So this portion here is for the parallel axis theorem. This portion here is just for the J prime. J prime plus area times radius squared. So that gives us 66.8 times 10 to the 6 millimeters to the, millimeters to the fourth, not millimeters squared. The other things we could do, so the chart from Shigley's. So we've got this chart here, given two parallel lines separated by distance. But again, like I said, if we just rotate, if we just kind of took these elements and rotated them in place, then that still gives us the same J. So, this setup where it is equivalent to this setup, basically. So just the values, you get the same values, you just need to plug in the B and D values for like the equivalence. So in this instance, the separation here would be kind of the distance between the center points of these two weld sections, because our situation is like this versus this. So the B value would be from here to here. So that's going to be basically that 250 plus another 100. Because basically half the distance of the weld on either side. So 350. So the B value we use is 350. The D value is just the 100 millimeters of the weld. So again, just plug that in there. 10.61 millimeters times for our thickness. Again, keep in mind when Shigley's gives you their J's, they don't give you the J directly, they give you the JU for some reason. So the JU is the unit J, and you need to multiply that by the thickness to get your J. So thickness times D times bracket 3B squared plus D squared, close bracket, divided by 6. So 10.61 times 100 millimeters times bracket 3 times 350 millimeters squared plus 100 millimeters squared, close bracket, divided by 6, which gives us, hey, the exact same value we calculated above. The other way we could go about this is basically we could calculate what the J would be for a big long weld, and then subtract the gap in the middle, the J for the gap in the middle. And we got that'd be basically the difference between this weld here, and then we kind of subtract this gap here when we have our actual scenario. So for that, again, we go to our B times H cubed over 12 formula. So for the kind of the long weld, it would be the B value would, well, for both of them, the B value would still remain the 10.61 millimeters. And the, I got a millimeter there, didn't I? And the H value would be the the total distance between the one end of the weld and the other. So that'd be 450 millimeters to the third. And then all that divided by 12. And then for the negative one, just, the size of that gap in the middle there. So 250 millimeters to the third times 10.6 millimeters divided by 12. And then that gives us, hey, the exact value that we were expecting to see. Isn't it convenient the way that works out? So a couple of approaches we could use to kind of find your J's. Which one you might pick kind of depends upon which one you're more comfortable with, whether or also some you might pick different approaches depending on the complexity of the weld complexity of the weld geometry in general. Anyhow, we got our J's, so we can calculate our stresses, our tau double primes. So tau double prime again is equal to mr over j. So we're going to be worried about kind of what's going on at the top and the bottom of the welds there. So that's where R is the highest. So that R distance there would be 100 millimeters plus the 250 divided by 2. So that ends up being 225 millimeters. So that's the point where we're going to be seeing the highest stress levels. And basically, because it's a rotational, we're applying a torque load here. So the forces that the loads that occur are basically acting in a direction that is perpendicular to the vector from the center to the point we're acting at, like always. And in this instance, because the point we're looking at and the center is vertically in line with one another, those are both in the x direction. So let's start plugging in values here. So our value of the moment, that's just the F, times that horizontal offset, which is 250 millimeters. So our our tau double prime, that's equal to F times 250 millimeters times the R distance of the 225 millimeters, and then divided by our J of the 66.8 times 10 to the 6 millimeters to the fourth. Everything cancels out to being, some of the millimeters cancel out, and then we're left with 8.42 times 10 to the negative 4 per millimeter squared F. So we got those stress levels in terms of F. So we can combine those two. And again, we don't just add them up because they're kind of acting in, they're forces that are kind of causing. They're the loads that are applying at at the local point. They're loads that are causing forces in different directions. So basically, we kind of just need to combine them. So we got this one that is acting in the x direction. We got the other one that is acting kind of in the y direction, and we're going to get some sort of resultant load, which results in some sort of resultant localized stress. So we combine those two, just the tau, the shear stress that we see is equal to square root of the tau prime squared plus the tau double prime squared. Now I just say tau prime squared and tau double prime squared because both those stresses in this setup are acting perpendicular to one another. That's a part of this setup. You're going to have instances where that's not the case, where you're going to have, say, some portion of the say the downward load was still applied, but the welds that we had looked like this instead. In that case, you're going to have a centroid here, and you're going to have the tau double prime stresses going to be acting perpendicular to the vector from the centroid to the point we're looking at. So you're going to have an x and y component to the tau double prime. So you're going to break that up, add the tau y component directly to the tau. Add the tau y double prime y component directly to the tau prime, and then combine that vectorially with the with the x component of the tau double prime. But anyways, that's not the case in here, so we can just we can just do that directly. So that ends up giving us a shear, a maximum a shear stress that is induced as a function of the load that we apply of 9.65 times 10 to the negative 4 per millimeter squared F. So we've got what occurs when we apply a load, so we can apply our failure criteria to this. So if we have the static load, and we're just told that the maximum shear stress that we see can't exceed 0.3 of the SU. So 0.3 times our 482 MPa can't be any higher than the stress we see can't be any higher than that. So that is equal to 9.65 times 10 to the negative 4 per millimeter squared F max. So again, we can solve for F max fairly simply there, and that gives us about 150 kilonewtons, 149.8 kilonewtons. So the other two failure criteria are both fatigue stress, or fatigue failures. So we're going to want to find what our SNS is for the weld material, our shear fatigue strength. So again, that is found just by finding what our, plugging in our CL for shear, like as if it was a torsional load. So our SNS is equal to SN prime times CL times CG times CS times CR. So, like I said, the CL that we should use for that, that's the 0.58 for shear load, basically. For a 15 millimeter size weld, we should be looking at a CG of 0.9. For CS, what we should do, we're going to want to be using the as forged line for that. When you weld something down, unless you specify that you're grinding it, or grinding and polishing or machining it afterwards, then basically the as forged line on your CS graph is the closest to what happens when you have a wilted melt pool that coalesces. So from there, again, our SU, I find that chart's easier to read if you know what it is in KSI. So it's 70 KSI. So looking at that, that's about 0.51. Again, I say 70 KSI because it's an E7010 welder rod. So the 70 there tells us what the ultimate strength is in KSI. So yeah, CS of 0.51 about. And then for the CR, they didn't specify otherwise, so let's use 1. And then our SN prime, again, that'll be 0.5 of our SU. So that'll be 241 MPa. So plugging everything together, that gives us an SNS of 64.2 MPa. So we got our S. We also have our SUS. So again, this is a steel. The ultimate shear strength of a steel is typically going to be 0.8 of the ultimate strength of the steel. So that'll be 386 MPa. And then the transmitting the yield strength to shear from the yield strength that we have is just attained by multiplying by the 0.58, and that's basically kind of like accounting for the von Mises equivalent of it in shear. So that'll be 240 MPa. So the graph didn't really show up too well here, so I'll kind of redraw it. So we've got the SYS line, SYS and the SYS line. Got our SNS and SUS line here for a given graph. So again, this is the tau mean. This one's tau average. And then we got the two loading lines. So we're basically going to have a loading line where if we're loading up the force from 0 to F, then basically, and going back and down from 0 to F, that means that our amplitude and our mean is the same. The average is right in the, we're going from here to here, the average is here, halfway, and the amplitude is, the difference there. So this would be the loading line for the 0 to F max condition. The loading line for the negative F to F, however, that one's just going up and down about 0. So our mean there is 0, and the amplitude is just the max. So I'm just going to draw it in red here. This is the loading line for the for basically the scenario outlined in C. So so varying from 0 to F max, our amplitude and our mean's the same, and that can be attained just by, we had this formula where we got the stress in terms of F. So we know that basically we plug in the F amplitude and the F mean into this equation. They're the same in this scenario, and they're equal to F max divided by 2. So the 9.65 times 10 to the negative 4 per millimeter squared is equal to the F max times F max divided by 2, gives us our tau average and our tau mean, and that is equal to 4.825 times 10 to the negative 6 millimeters squared. It's 10 to the negative 4. Sorry, it's a bit hard to read there. Per millimeter squared F max. So that line really didn't show up well. So we got our failure criteria. 1 over our factor of safety is equal to Kf times tau average divided by SNS plus Kf times tau mean divided by SUS. Now the Kf that we should use here, let me grab the Let me grab the lecture here real quick. Okay. So looking at this, we could basically the two loading scenarios that we might consider. Got the parallel loading and the transverse loading. Now we know in this situation, so the welds look like this, and we're pulling down on it like this. So at least that's causing stresses that are kind of oriented this way and oriented this way. At least some portion of the stresses, of what's going on here is a parallel loading situation. So I think we should use the worst case scenario and just assume it's all parallel. Assume that the stress concentration that occurs is equivalent to all of it being in a parallel loading situation. So I'm going to use the 2.7 throughout for this problem. So yeah, 1 over 1.5 is equal to 2.7 times the 4.825 times 10 to the negative 4 times F max. All that divided by our SNS, so the 24.2 Newton megapascals, so or newtons per millimeter squared for the purposes of canceling stuff out, because those millimeters there, millimeter squared here cancels out with those millimeters squared, plus another 2.7 times another 4.825 times 10 to the negative 4 per milliliter squared times F max divided by our SNS this time, the 386. That gives us, that allows us to solve for an F max of 28.1 kilonewtons. So if we're going from negative F max to F max, however, we're going from here and up to here and then back and forth, then again the mean is going to be 0 and the amplitude is just the maximum stress that would be occurring. So that simplifies the calculation a little bit because we're able to get rid of one of the terms. So 1 over the safety factor is equal to Kf times tau alpha, tau amplitude divided by SNS. So based upon that, we can solve for what our F max would be. So for our maximum F, if we're going from that value up and down, is going to be equal to the 16.4 kilonewtons. So that situation is worse than if we, where it's all amplitude is worse for fatigue than if we had some amplitude and some mean. And again, that's because we're seeing the same stress levels. If we were seeing, the same load levels, and we're just kind of varying when we're going all the way up and down. So basically, on the Goodman graph, we got kind of, load line, yeah, it might look something like this versus a load line. That basically, if you have the same length of the yeah, if you're splitting up it into amplitude and mean components, your load line for the other one would look like this, where like this value here is twice this value here. So basically, kind of the length of this line gets a bit shorter. So that kind of accounts for the fact that kind of accounts for why we get a smaller max allowable load for the amplitude only situation. That's different than if we kind of kept the same amplitude and just added on some mean stress. So if we keep the amplitude the same and add the mean stress, add something like this instead, then obviously that line is going to be a lot closer to its failure criteria than this line would be. So we'd end up having a lower allowable maximum load in order to attain the same safety factor there. Yeah, that's that. So next we'll do an out of plane bending scenario, and then there'll be one more example where it's combining all three. That'll be fun.